As Christine said, good evening. Welcome everyone to this MAVEN Outreach webinar. My name is Tom Mason. I'm the manager for communications and outreach at the University of Colorado's Laboratory for Atmospheric and Space Physics. As I indicated, I put a URL in the chat, and you can access this webinar and all previous and future webinars at that address if you care to do so. Now I'll introduce our speaker for this evening, Dr. Rob Lillis. We're excited to have him here and hear his talk. There's been a lot of interest in this topic, I know, and I'm sure Rob will give you more details. We did have a recent paper come out from the MAVEN mission, the principal investigator for the MAVEN mission, about this very same topic. So it's a very topical subject. So Rob is an associate research physicist at the University of California, Berkeley Space Sciences Laboratory in their space physics research group. His research interests include planetary atmospheric evolution, ionospheres, and paleomagnetism. Rob is involved in the data analysis and modeling of plasma and magnetic processes in the Martian atmosphere, and the geophysical implications of subsurface magnetization. Rob received his bachelor's degree in theoretical physics from the departments of mathematics and physics at Trinity College, Dublin in Ireland. And he received his master's and PhD degrees from the University of California, Berkeley Department of Physics. Rob is a MAVEN co-investigator, and he's involved in synthesizing MAVEN science data and producing models that extrapolate Mars's escape rates over time. You can correct me if I'm wrong about that, Rob, but that's my understanding. Rob, thanks for being here. And as I mentioned, I'm really looking forward to hearing your talk.
Thank you, Tom, for that great introduction. Much appreciated. And apologies to everyone who tried to tune in 3 weeks ago when we had to postpone this. That was to do with the paper that Tom had mentioned earlier, and a press embargo on it because it was too closely related to this topic. Anyway, here we are today. So let me, can everybody see a PowerPoint screen in full screen mode?
Yes, although, yes, we can. Thank you.
Okay, okay, good. Okay, so let me just get started. So as an introduction, thanks everyone for coming to this webinar and for showing some interest in where some of your tax dollars go and where maybe a lot more of them might go in the future. So Mars has always been sort of in our collective cultural imagination ever since the first published sketches that Percival Lowell made from his telescope more than 100 years ago of what looked like these aqueducts of a dying civilization. But in the last few decades, as we've sent robotic explorers across the solar system and technology has advanced unceasingly, and as human populations have continued to rise rapidly, it's become natural to speculate on when and how humans will eventually venture away from the Earth, not simply to visit, but perhaps to live and to continue with several generations. And Mars has been a natural place to look here, the nearest large planetary neighbor that we could realistically imagine living on, with its approximately 24-hour day and moderate gravity and seasons and mountains and valleys. But because we humans enjoy breathing and liquid water and things like that, today I'm going to talk to you about one of the most important aspects of any planet that we might consider living on, the atmosphere. I'll tell you about Mars' atmosphere at the present, in the past, and possibly in the future if we decide we want to mold it to our liking. Which brings me to my title, which is Resurrecting the Martian Atmosphere. Why might we need to resurrect it? And the answer is because you were lied to by Hollywood, which is completely unsurprising, but you were lied to. The movies like The Martian, which show this dust storm and the astronauts walking with great difficulty through it, it's completely unrealistic because the Martian atmosphere is much thinner than that. So this isn't real, but this might be someday, the idea of cities on Mars. So just to go over Mars's, some of the basic features of Mars's present atmosphere and climate. It's a mostly CO2 atmosphere, very low surface pressure, just 6 millibars, less than 1% of Earth's atmosphere, and it receives just over half-ish, it depends on the time of year, less solar radiation than the Earth. So the average temperature at the equator is about -60 centigrade, and at the poles -120. So it's very, very cold. And liquid water is not stable on Mars because the pressure is too low. So in other words, thin, cold, dry, and poisonous, and also too thin to stop cosmic rays from penetrating down to the surface and giving you cancer over time. Was it always like this? As we all know, nope, no, it wasn't. And there's plenty of evidence for Mars having a much thicker atmosphere in the past, an atmosphere thick enough to support liquid water. We have these flood-carved channels on the surface, 1,000 or more kilometers long. We have evidence of lakes that formed within craters, and then ice dams that burst, and then the water flowing out across the surface. And then we also have these so-called valley networks, which look sort of dendritic, as though they were carved by rain falling and then flowing down and flowing down from the higher elevations. And then in addition to that evidence from orbit, the Mars rovers, Spirit, Opportunity, and Curiosity have found abundant evidence for ancient liquid water on Mars more than 3.5 billion years ago. We have things like mudstones in the floor of Gale crater that Curiosity saw. We have these little blueberries that Spirit found. Those are blueberries that's what they're called because of their size and shape, made of hematite, which is formed from precipitation from mineral-laden water inside rocks, and similar features have been seen on Earth. We have these layered terrains where layers of sediments were laid down in a wet environment. We have this hydrated silica that was found by the Spirit rovers, and we also have this so-called festooned cross lamination, which is essentially the remnants of underwater sand dunes. So we had all that water. So where did the water go? Where did the CO2 go that formed Mars's thicker atmosphere? So liquid water isn't stable on the Martian surface today because the pressure is too low. But even at higher pressures, it's too cold for water to remain liquid in enough places for long enough to explain these features. So there must have been a thicker, warmer atmosphere. And the question is, how much thicker, how much warmer? There's only two places that CO2 could have gone. It could have either gone down into the crust, and there are evidence of carbonate deposits. This is one here shown in a Martian meteorite, a rock that came to Earth from Mars. And then also volatiles such as water and CO2 can be lost to space, and this is a simulation of oxygen ions being stripped away from Mars by the solar wind's electric field, and I'll talk more about that soon. So in terms of the volatiles going up and down, we certainly do know that some of the volatiles went down into the crust because we have abundant evidence of aqueous minerals produced by interaction with water. The so-called phyllosilicates shown there in blue are all aqueously altered minerals. We also have carbonates. Carbonates are minerals which can store carbon dioxide, but those are comparatively rare compared to the aqueous minerals. And optimistically, and I'll get to this more later, they might store between 20 and 50 millibars of CO2, and this was the subject of the paper that Bruce Tchaikovsky, the MAVEN PI, published with Christopher Edwards recently. Okay, so where has that atmosphere been going? It's been leaking away for billions of years, and this was the reason why NASA sent the MAVEN orbiter to Mars, to understand the processes of atmospheric escape, to measure the escape as it's happening and measure the relationship between that escape and energy inputs from the sun, both in the form of ultraviolet radiation and the solar wind. And this is an animation showing MAVEN's orbit. MAVEN's orbit takes it close enough to Mars to measure the physical processes taking place in the atmosphere that drive the atmospheric escape, but also far enough away to get a global view of that atmospheric escape. And so that explains the elliptical orbit. a number of different physical processes can cause atmospheric loss, and shown here on the left again is that same animation showing what happens to ionized oxygen in the Mars upper atmosphere as it gets stripped away from Mars, both in this sort of polar fountain that looks a bit like a mohawk on top, but also kind of a stream going back behind the planet. And then on the right was a diagram that went into MAVEN's original proposal, and we don't need to go through everything here, but just to say that there's probably at least 5 different atmospheric loss mechanisms, and the MAVEN science team is still hard at work understanding what all those are and how they depend on those solar inputs from the sun shown on the top left. One thing we have figured out for MAVEN for sure is that the rates of atmospheric escape increase with solar ultraviolet radiation and solar storm activity. And this is just an example of this from a paper I published last year with the solar extreme ultraviolet flux at Mars on the x-axis and the escape flux on the y-axis, just showing that there's a positive correlation between the two. And as well as that, we also know that the early sun was much more active than it was today, with a far higher solar ultraviolet irradiance. And this is from a plot from a paper by Rebus about 13 years ago, showing where we are today in terms of solar UV flux and where we were 3.5 billion years ago. And as you can see, it was much higher. So combining what we've learned from MAVEN today and how it depends on solar UV radiation, and then knowing how much stronger solar UV radiation was back in the past, we can estimate that several hundred millibars, and 1,000 millibars would be equal to the Earth's atmospheric pressure today at our surface. So a substantial amount of atmosphere has escaped over Mars's history. Okay, so we've lost a lot of atmosphere, and there's not a lot of obvious CO2 that's gone, that's in the visible surface rock. So if we did want to start thinking about resurrecting the Mars atmosphere, what can we do? Okay, so before we sort of dive into what it would take, let's just go through the checklist. And this is a bit of a tongue-in-cheek checklist here, but it's I believe it's not inaccurate. So first of all, honestly, I think we need really a fanatical will to succeed, and you'll see that as the slides go on because of the sheer difficulty of doing this. And I think the only people who are actually going to want to do this are folks already living there. I don't think people on Earth are going to have the money or time or patience to actually go and do that. So I think it'll really take people deeply invested in it to do it, and hopefully it'll be humans, but robots are there too. Hopefully they won't take over. So yes, the will to succeed is one. It'll take a lot of money, many dollar signs. And this is just some funny GIFs here that I've done here, and Dr. Evil asking for $1 million. It'll be a lot more than that, probably pretty many hundreds of trillions, but it's a difficult number to estimate. Energy, just an awful lot of energy, and I'll get to that too as the slides go on. But wind farms on Mars are not going to be enough. There just isn't enough energy contained there. Same thing with solar panels. Here's Matt Damon clearing the dust off his solar panels, also not going to be enough. I think the only thing that's going to suffice is going to be nuclear energy, and an awful lot of it, probably tens of thousands of nuclear power plants built on Mars, and I'll get to why that is a bit later in the talk. But energy is a huge piece of this puzzle. And then patience, like, you know, extreme patience, knowing that your great-great-grandchildren, you know, might see it sort of just get going, that kind of level of patience. And then also a large quantity of the right elements to make an atmosphere that are readily available on Mars, things like methane and CO2, which are greenhouse gases. And I'll get to that as well. Okay, so let's go through some of the practical steps that you could take to start thickening up Mars's atmosphere. So the first thing is, the kind of quote-unquote easy part, is that the south pole of Mars is made up mostly of dry ice, carbon dioxide ice. And this will sublimate into the atmosphere if it's heated by a few tens of degrees. So if you're able to do that heating, you can sublimate some of the CO2 away. That leads to a higher CO2 pressure, leads to an increased greenhouse effect, leads to higher temperatures, leading to more sublimation, and the virtuous cycle continues. And in this way, we think that about 12 to 14 millibars of CO2 could be released, which would triple the atmospheric pressure from what it is right now. It's still an awful lot of heat, and it's not clear where that heat would come from. People have said, well, maybe we could just nuke the South Pole with an H-bomb. It would probably want to do that before the colonists, or at least far enough away from where any of them might live. Other ideas include digging so-called moholes, so-called because they would be reinforced holes going all the way down to the moho region, which is the region of the crust where the sort of upper brittle crust becomes more ductile and transitions in to the mantle. And these would be sort of a kilometer wide and 7 to 10 kilometers deep, and they'd be really hot down to the bottom, and they would release hot air continuously. This was popularized in the Red Mars book by Kim Stanley Robinson. You could just build fusion power plants to slowly melt the CO2 ice there. You could put orbital mirrors to reflect sunlight down onto the caps. These are different ideas people have had. Second thing you have to do, and let me make it clear here that I'm talking about how to terraform Mars sort of with technology that we understand right now, things that we know how to do right now, even if they're at a very large scale. So the second step is we need to dig up an awful lot of just material from Mars. And the reason is that every single square meter of Earth's atmosphere weighs about 10 tons. If you were just to take a square meter and go all the way up to the top of the Earth's atmosphere, that weighs about 10 tons. And Mars has about as much area as all of Earth's continents combined. So we need to dig up at least 10 tons of rock for each of the 144 trillion square meters on Mars. So that's a very large amount of material. So if you think that crustal rocks are about 3 tons per cubic meter, we need to dig to an average of 3 meters over the entire planet. Likely we would just dig to a much greater depth in a much smaller area. Maybe we could use the tailings from digging these moholes. Still, 1 million billion tons of rock, 10 to the 18 kilograms, is a huge amount of rock to dig up. Okay, so if we've dug up all this raw material to make an atmosphere, how do we actually go and do it? So like I mentioned earlier, getting CO2 from the poles is about 1.5% of what we need. That's a start. There's probably about an additional 4% adsorbed in the regolith in the form of CO2 around the planet, and this is something that Bruce and Christopher mentioned in their paper. But to actually release it, you'd need to dig at least to sort of disturb the soil to about 100 meters planet-wide to release it. So it's unlikely we could get much more than a small fraction of that out. Maybe what's more realistic is to liberate oxygen, hydrogen, carbon, nitrogen, the different atomic constituents of an atmosphere by vaporizing the rocks that we've dug up and then releasing it. And this is an idea people have also looked at before. But in order to do that, we need to vaporize 1 million billion tons of rock. And that's just really, really hard. That takes an enormous amount of energy. If you just do some simple math, if you take that 1 ton of rock takes about 3 gigajoules of energy to vaporize. So one big nuclear reactor, and they're on the order of a gigawatt each, could vaporize a ton of rock every 3 seconds, or about 10 million tons per year. But notice there's still another 8 orders of magnitude to get up to 1 million billion tons. So we need 10,000 nuclear reactors running for 10,000 years in order to vaporize all that rock necessary to make an atmosphere on Mars with the same pressure that we breathe on Earth right now. And note also that 10,000 nuclear reactors is about equal to Earth's entire electricity output at the moment. So this is no small deal. People also have talked about, well, couldn't we think about using comets instead? I mean, it's a pretty huge undertaking to build all those nuclear power plants and to vaporize all that rock. So couldn't we use comets to help? And there's various ideas for what it would take to sort of turn a comet to change its orbit. Various ideas are things like put a small nuclear reactor somewhere on the comet and build a funnel and turn the ice into steam and blast it through that funnel as a rocket to steer the comet. And this was popularized in Neil Stephenson's book 7 Eves recently, and it certainly is a feasible way to go. It would take, of course, minimum decades, if not hundreds of years, to actually turn most comets and get them to impact Mars. And also, we need a lot of them because comets weigh between 1 billion and about 100 billion tons. Halley's Comet is at the upper end of that. It's about 100 billion. So we'd need to crash between 10,000 and a million comets into Mars to just create enough mass, and then hope that most of it is actually, and then also do it carefully, like maybe bring them into a low orbit and have them enter the atmosphere slowly, so that all of the water is not lost at the top of the atmosphere during the impact. So it's difficult, but it's probably something that could be done. And as I note there, most comets are in these very long, far, slow orbits, so this is going to take many centuries to happen. It's probably too many for humans to do themselves, but advancements in technology such as autonomous in-space assembly of spacecraft and of these sort of ice funnel, or the equipment needed to make these ice funnel rockets, or these ice and steam funnel rockets would be needed, and also autonomous navigation, so that all of these robot spacecraft could find their way to the comets themselves. So there's a lot of technology that we don't have right now that would be needed to use comets. Okay, so let's say that we were able to do all that. What gases would we want to make the atmosphere out of? So we can look at CO2, and CO2 is an effective greenhouse gas to get things going. But as we said, on Mars itself, there's probably not more than 50 millibars available, sort of 5% of the way there. And also, its greenhouse advantages really diminish once you get above about 100 millibars anyway, and it's kind of poisonous to humans. So we wouldn't want that one as our main gas in the long term. If we look at oxygen, there's certainly plenty of it in the Martian rocks. If we were to vaporize it, and we could certainly, it would be the main H2O that we would bring in comets. We could have oxygen from that, but we wouldn't want it to be 100% oxygen, because things would be extremely flammable all the time, and that would be bad. We wouldn't want the atmosphere catching on fire. Nitrogen would be great, but unfortunately there's very little on the surface of Mars. There might be more deeper, we don't know, but we don't think that Mars has very much native nitrogen at all. So that doesn't look like a good option. We could bring some from Titan, perhaps, if we could figure out how to do that, but that's an awful long way away. Last thing is we actually need to warm up the planet. Mars is much further from the sun, so we'd need about a 70-degree greenhouse effect, and CO2 is not that good past a certain point, as I mentioned earlier. Methane is 80 or so times more efficient than CO2, but we still would need too much of it for it to be practical, and plus it's poisonous as well. A better potential solution is that there is some research that has shown that a cocktail of fluorine-based super duper greenhouse gases could keep Mars as warm as Earth at very, very, very low levels, 200 parts per billion, or 0.00002%. And that's probably practical. That could be maintained with a current Earth level of mining activity on Mars. So that part is probably doable. Okay, so we've gone through these various steps, none of which are easy, some of which are harder than others, and which will definitely take enormous time, energy, effort, money. But I would say let's not get ahead of ourselves, and let's look at some of the prerequisites to even starting this kind of endeavor. The first thing, I think, is to send humans to Mars and to bring them back safely, so that others might want to go. If we can't do that, then I think the whole thing is kind of mute. And then after we've done that, send more of them to Mars to actually live, and make sure we keep them alive there, and then more of them might go. I think the most difficult piece of this is getting from that small little outpost size of settlement, the sort of dozen or so people, to the kinds of tens of thousands of level that starts to become possibly self-sustaining, or at least more self-sustaining, and with a sufficient workforce of people that will actually perhaps want to dedicate their lives to an endeavor like terraforming the atmosphere. And I guess that's what I just said. Yeah, establish a Martian society that's large enough and robust enough, with folks who actually care enough to start this. Because, like I say, people on Earth are not gonna want to spend the money or time taking on this Herculean task endeavor. And then I think wait for large technological advancements in space travel, so that we can bring materials cheaply from the Earth. Like I said, the technology required to steer comets to crash into Mars, things like automated industrial production and mining, so that we would just have robot mining trucks and robot mining machines that can mostly manage themselves and just get on with the task of digging up the huge amount of material needed to terraform the atmosphere. And then, I mean, I guess all of those sort of fall under geoengineering, but geoengineering can also mean things like putting mirrors in orbit around the planet, and there's other crazy ideas along the same line, again, from some of the science fiction books, like putting a set of orbiting mirrors around Mars that would essentially provide a larger cross-sectional area so that Mars could absorb more sun than it does now, and to reflect that light down onto the planet. Another way to bring more warmth to Mars. So when we think about the sort of long-term prospects of actually doing this, there's a few questions to ask. I mean, when will space travel and supporting the Mars colony really get cheap enough that this is something that sort of becomes an obvious thing to do? I think the price tag for people moving to Mars has to be right, and I know that SpaceX has said that they're intending it to be no more than a couple $100,000, but even that is a substantial price tag for most people. So I think we're a long way from getting the price tag down to that kind of level, but we shall see. Other issues. I mean, if you live on Mars at the moment with the thin atmosphere, you need to spend most of your time underground, or at least inside very, very thick domes that are essentially double hulled with rock in between the two hulls, a couple of meters of rock. And in the meantime, unless we want to be consigned to spending 22 hours a day underground, if we want to be able to spend weeks and weeks at a time exploring Mars, when are we going to be able to fix the medical problems inherent to living on Mars, like DNA damage from radiation? And I'm definitely, biological technology is advancing on that front too, and that'll probably happen eventually, but we're not there yet either. And then, like I said, will the society be stable and robust enough to actually grow to the kind of size needed to start this process of terraforming? What kind of society is it going to be? Do we have capitalism? Is it more collectivism? It would certainly be collectivism when it's very small, but as any society gets large enough, so large that people don't know each other as well anymore, something like capitalism would probably have to come in. It's been shown to be an effective motivator once societies are large enough that folks don't know each other. But there's questions like, do people have to pay for their air? I mean, would Mars want to become independent from Earth? Is that going to lead to conflict? What about anti-immigrant sentiment? All these sorts of societal questions will have to be answered as well before the Martian society is able to undertake this huge task of terraforming. And just one more time, these atmospheric raw materials, do they exist in sufficient quantities? I think the nitrogen question is a really, really big one. Maybe we can ship it from Titan, but that's just an enormous endeavor as well to basically steal most of Titan's atmosphere and bring it to Mars. That would be a truly titanic task. And I think there's a lot of unknowns here in terms of the atmospheric raw materials. So just to kind of wrap up, looking at the big picture of this, I think it's true that with truly colossal amounts of cumulative will, money, time, and technological advancement, it seems to me that we could make Mars habitable for humans. But the unknowns, and there are many, there's known unknowns and unknown unknowns, to quote Donald Rumsfeld, make the timeline somewhere from many hundreds of years to possibly never, depending on the practical difficulties of getting the right raw materials. So I guess watch this space. It's certainly an exciting time to be in this area with companies like SpaceX planning planning missions to Mars, with NASA planning human missions to Mars. I know that NASA recently, just with their most recent class of astronauts that were chosen last summer, the first ever Mars PhD was there, which tells us that NASA is actually serious about sending people there. So it's an exciting time, but in terms of the long-term transformation of the atmosphere, I think we should be patient, very patient, because it's going to take quite a while. And that was all I had to say. Yep, that's it.
Awesome. We have a number of questions already. So Diane wanted to know whether asteroids could be used as space station outposts and move where we want them to go. Would that help with this problem?
Certainly, the kinds of technology that we'll need is technology that we could perfect on asteroids. Was she specifically wondering whether we could make outposts around Mars using asteroids? I'm not.
She didn't specify, but if you'd care to comment on that, that would be interesting as well.
Okay, well, Mars already has 2 asteroids orbiting it at the moment, Phobos and Deimos, and a lot of the thought that's gone into how humans would go to Mars and live there is that there would be an orbiting outpost there, a useful kind of first place for humans to go, and eventually possibly as an anchor for a space elevator, given that both Phobos and Deimos are on the Martian equator. So yes, I think asteroids and making asteroids into little space stations could easily play a part in this.
And then the next question was, so since Mars lost the bulk of its atmosphere when it lost the bulk of its magnetic field, and the solar wind stripped it away, the low gravity there isn't helping with holding onto an atmosphere. So if Mars now had a complete atmosphere of 1 atmospheric pressure, how long would it be before it dropped again to half an atmosphere?
Oh, it would last many, many millions of years. The rate at which Mars loses atmosphere at the moment is on the order of a kilogram every 5 seconds or something like that. It's a very, very low rate of atmospheric loss. And so we could certainly build it up much faster than it would leak away. Much, much faster.
And Sally asked if it's an international endeavor or mainly the U.S. I don't know if she's talking about this possible futuristic concept of building an atmosphere, or if she's specifically talking about MAVEN.
Oh, well, I can answer that in 3 different ways. One, I think MAVEN is mostly an American effort. There's a contribution of half of an instrument from France, but there are MAVEN team members across the world. In terms of NASA's general more broad Mars program, I think there's a recognition that this is too big for any one country to do by itself. The U.S. could do it, but it would be an enormous outlay. And I know that for the upcoming Mars sample return effort, recently NASA and the European Space Agency signed a memorandum of understanding to essentially split up that task into easily separable pieces. And then more broadly, when NASA talks about sending humans to Mars, it generally does consider that it will be an international effort with, if to spread the cost, if nothing else. And also, I think the more countries that are involved in it, the more countries that have truly signed up to it and are invested in it, the less easy it is for politics in one country to kill it. So you can imagine if it was just an American effort and it was going along, and then there was some new president who decided that it was a vote winner to kill this, it could be killed. So I think having it spread across a number of countries could make it stronger, and I think that is how most people are thinking about it.
Awesome. There are several others. Let's see. There was a question back to asteroids. Diane wants to know the idea of slingshot moving asteroids.
Do you mean using asteroids to change Mars's orbit and bring it closer to the sun? Is that what the question is about?
I don't know if it's well. she didn't specify moving Mars closer to the sun. I suspect she means slingshot, actually moving asteroids to create the atmosphere instead of, yeah.
Oh, I see. Right, right. So instead of using comets, using asteroids to increase the atmosphere. Well, the thing with that is that if you were to bring, even if you were to redirect an asteroid to impact Mars, only a very, very small fraction of that asteroid, well, I guess even if most of the asteroid were to vaporize, you'd still have the same issue you do with the comets, that you'd need to bring a truly enormous amount of asteroids to Mars in order to do that. So yes, that could be a part of it. I mean, there's probably some ideal composition of atmosphere that we want, and maybe it's a combination of asteroids and comets that we could redirect towards Mars in order to sort of make that ideal cocktail of atmosphere that we're looking for.
Okay, a couple of these are related. Well, one of them here, magnetic field, says, "What would, without a magnetic field, how would we keep the sun's radiation from blowing away everything that's created?"
Okay, so there's a bit of a misconception here, I think. First of all, magnetic fields, they form a shield that keeps much of the solar wind away from touching the upper atmosphere. That's also true on Earth. However, even without a magnetic field, like I mentioned, the rates of atmospheric escape from Mars today are so low that it would not be a substantial loss of atmosphere. It would still only be on the order of a few kilograms a second at most, and we'd be able to produce atmosphere much, much faster than that. Second of all, thinking on the topic of whether a magnetic field actually helps or hinders a planet from keeping or losing its atmosphere is actually evolving, and it's not clear that a magnetic field does result in less atmospheric escape. And the reason is that if you have a global magnetic field, that global magnetic field, just like Earth's, stretches way, way, way out into space, far beyond the planet itself. And it acts as an obstacle to the solar wind, a much larger obstacle than it would be if you had no magnetic field. And so all that energy that is essentially being absorbed from the solar wind tends to be concentrated down into the poles, into the magnetic poles of the planet, and can actually result in much, much higher atmospheric escape rates at those poles, perhaps even higher than it would be if the planet had no magnetic field at all. So this is still a really cutting edge, bleeding edge topic of research right now, and also debate among planetary scientists. Does a magnetic field actually reduce atmospheric escape rates? We're not sure yet.
Great. So let's see. There was a question about radiation. How do we mitigate the radiation problem in transit to Mars and during colonization before you can actually make underground facilities?
That's a really good question. I think what you'd have to do is you would have to at first, you just have to accept the fact that it's going to take a while to build your underground habitat. And so you're just going to have to accept a somewhat higher risk of cancer for those, hopefully not more than a few months while you're building your habitat. And so the astronauts going would have to just be okay with that, because the particles on the surface of Mars that provide that radiation are such high energy. These are galactic cosmic rays. There's really nothing that you could do in terms of wearing a suit that would actually stop them. The only thing that can stop those is a couple of meters of rock. Similarly, if you're in transit to Mars, you also can't stop those high energy rays. What you can do is, because the other source of damaging, ionizing, cancer-causing radiation, and maybe even death-causing radiation, are solar energetic particle events. And once every 10 years or so, the sun will belch out a really high energy and high flux event that could actually kill an astronaut. So, but those particles are lower in energy, and so those particles actually can be blocked by a relatively well, at least a practical to build kind of a shield. And so you could think of the colonization ship on the way to Mars having a storm shelter, and the crew getting a few minutes of warning that a deadly dose of solar energetic particles was coming, and all of the crew could go and hunker down in this little closet that's lined with lead, or even just lined with enough water, and they could stay there for 2 or 3 days and kind of wait it out. And the same could be true of the habitat on the surface of Mars before the underground dwellings are built. But yeah, it's a good question.
And based on some of the questions, I'd like to invite you to clarify the status of current plans and your own thoughts on the probability of plans for any of this.
Okay, so, well, let's just, I guess I'll answer that in two different parts. The status of current plans. So there's a difference between something being in various, something like Mars, something like human missions to Mars being in a goals document, and it certainly is in NASA's goals documents, and it certainly is in the kind of corporate literature of a company like SpaceX. It's very different from actually money going into the budget and being kind of like agreed to and signed on the dotted line. And currently there's a lot of money being, invested in the Space Technology Mission Directorate in order to enable human crews to go to Mars. And like I said, there are now astronauts who have been picked, who've been picked specifically because of their Martian expertise. There's also a plan, as far as I'm aware, and plan is a vague word here, but if you consider the political reality that NASA's total budget of about $21 billion a year, it can go up slowly, but it really can't go up by a very large amount unless we had a president and Congress that really, really, really wanted to inject a lot more money into it. The fact is, every dollar in Washington is, sort of hoarded and fought over. So if you consider that NASA's total budget can't go up, then the only way to really make the Mars mission happen is for NASA to let go of its obligations to keep funding the space station, because that's several billion a year. If the US after 2024 decides to no longer support the space station and transfer it into private hands or let the other countries deal with it, then that would free up enough money that it would be reasonable to send humans at least to Mars orbit by the early to mid 2030s. So NASA does have those kinds of plans in mind, but they're not actually in budget documents that have been approved by Congress yet. The wider question of whether this will all happen at all, I think this is a really interesting time to be considering these questions, because ever since the 1970s, ever since the last of the Apollo landings and then the landings of the Viking spacecraft on Mars, humans to Mars has always been 20 years in the future. In 1975, they would have said, oh yeah, by the early mid-90s, we'll definitely have done this. And then if you were to ask the question in 1985, they would have said, oh yeah, by 2005, yeah, sure. And it's always been 20 years in the future. And then every 10 years or so, some politician would say, yeah, let's do this. And then they'd have a look at the price tag and be like, oh, no, just kidding. And I think what's happened in the last 10 years is that technologies have actually come through that are starting to make this more of a reality. And companies like SpaceX with reusable rockets are sort of a big part of that. So I think there's an energy and a momentum behind sending humans to Mars now that I've never seen before. And so I'm reasonably hopeful that it'll happen. Might it take 10 years longer than we think? Might it be 2045 instead of 35? That's entirely possible, but I do believe that it will happen within my lifetime.
Awesome. So I'm going to combine two questions here. Do you think the moon will play a role in this endeavor? And do other countries have different ideas about where we should be going to live?
Okay, so the moon part. So the moon has often been sort of raised as a useful training ground for sending people to Mars, because the moon is close enough to the Earth that you can talk in real time and you can get there and get back within a couple of days. And different U.S. administrations have kind of been bigger or smaller fans of using the moon as a stepping stone, and others have said, no, let's go straight to Mars. And so I think this administration again does want to use the moon, and this is just a function of the opinions of the sort of senior space people who happen to be in each successive administration. The moon certainly can play a part. I think there's probably lessons that we can learn. There are different environments. You don't have this kind of sharp quartz sort of dust that you have on the moon on Mars. In terms of do different countries have different opinions? Well, there is a group called IMIWIG, or the International Mars Exploration Working Group, and they meet I believe it's every 9 months to sort of coordinate approaches. And it's not, I know that IMIWIG deals with not just robotic and scientific exploration, but also potentially human exploration. So if other countries have different ideas about where on Mars to go or how to do it, they can raise those points in that forum, and depending on how much money they want to contribute, they could implement those things. If the question was referring to where else in the solar system we might want to live, I'm not particularly aware of any one country saying, no, we shouldn't live on Mars, we should live on Europa or Titan. I think everyone kind of agrees that Mars is the most obvious place to go for the reasons I mentioned early on in my talk, with things like the 24-hour day and the seasons and all that. And yeah.
Thanks. There's a question about whether what type of spacecraft itself could be used as a shield for the initial crew going, when you were talking about radiation.
Yeah, well, I mean, certainly the SpaceX Mars ship called the BFR, the Big Falcon rocket, that's certainly large enough that you could imagine putting a radiation storm shelter inside it somewhere, probably towards the middle of it, so that just the hull provides even more protection. So yeah, that could, and there's no reason why that initial ship couldn't also form the basis of a habitat for the first couple dozen people as well. I think SpaceX has an idea that those ships would actually just go back and forth, and think they've been designed by SpaceX as a transportation mechanism. I don't think they were specifically thinking of using them as habitats, but that's certainly one of the options on the table for the people thinking about this.
Okay. So a question that's very MAVEN specific. So if a global magnetic field didn't turn out to make a big difference, or makes little difference, is there anything besides Mars's lower gravity and the lack of replenishing due to extinct volcanoes that has led to the atmospheric loss? And what about the idea of the solar wind getting close enough to Mars to ionize the upper atmosphere more than what happens on Earth?
Yeah, so I think those are, the question incorporates all the pieces that are sort of responsible for the sort of pluses and minuses, or the sources and sinks of the Mars atmosphere, and how we think about how they each varied over time. Certainly, I think the character of atmospheric escape would have been different when Mars had a magnetic field, but like I said, it's not clear that the total rate of loss would have been that different, and that's partly for the reasons I mentioned, and partly because at least two of the major atmospheric escape mechanisms don't really care about a magnetic field. Hydrogen escape from the top of the atmosphere, which is higher when it's warmer, doesn't care about a magnetic field, and then the second most important escape mechanism, or so-called photochemical escape of oxygen, which is where chemical reactions that just naturally occur in the upper atmosphere result in hot atoms that can escape Mars' atmosphere. Like I just said, I think the sources of atmosphere and how they change over time are very important, because as the questioner mentioned, as Mars's volcanic activity died down and down and down and eventually went to almost nothing, that source of atmosphere kind of dried up. And so I think understanding in more detail the history of Mars's atmospheric production from volcanic outgassing is going to be a big part of this. But in terms of anything else, I think there are other things like oxidation. If Mars, started out as a planet that was not very oxidized, as it oxidized, that would have absorbed oxygen out of the atmosphere. Whether Mars had enormous glaciers that could trap water. There's all sorts of planetary processes that can trap and then release atmosphere over time, and it's sort of unraveling how all of those changed. That's going to be the key to doing this. I don't think we even have a firm grasp on how that happened on Earth over the course of the lifetime of the planet. So yeah, more work needed.
Okay, and then back to colonizing Mars. Are the societal logistics for Mars colonization or habitation being proposed by a dedicated team of anthropologists?
Not a team that's being paid by any space agency. There could well be people who are interested in this and who may have drawn up, white papers about how you deal with the specific challenges of being so isolated, and then the sort of interpersonal dynamics, and then how that leads to a larger society, and how you motivate that society. What sort of system of money do you use? Do you use money at all? All those sorts of things are important. And I think it's a team of anthropologists, microeconomists, sociologists, psychologists will probably need to study this at some point, because there's a lot of potential stumbling blocks between that first landing and having a really robust, stable society that would ever want to undertake this huge endeavor of terraforming.
Absolutely. So, if microbial life is discovered on Mars, how would that affect our willingness to colonize, thereby disrupting that Martian life?
Yeah, this is a big question, and it's really a balance between the sort of ecological and scientific concerns and the desire to have humans live there. Because it's true, if we were to discover microbial life on Mars, I think at the very least you'd want to put humans landing on Mars, or certainly colonization, on hold until you could really understand this. And maybe the best way to do that would be to send a small team of people and make sure that they don't contaminate it. I think it depends what it's like. I think if it has a very different kind of DNA than we do, that's very easily identified, then you wouldn't have to worry so much about contamination just from a few humans going there. You could study it with human biologists, but I think this is going to be a very it's going to play out in much the same ways that people tend to have strong opinions on both sides of the development versus conservation question on Earth. But except on Earth, those people are called greens. On Mars, they might be called reds, because that's the sort of natural background color of the planet. But I don't have one answer there. Certainly wait long enough to learn as much as you can, but I don't think you can hold up colonizing Mars forever.
Well, those are all the questions I think that were posted. There's a couple that I kind of answered myself a little bit. But if other folks have other questions, please go ahead and type them in now. Or if you don't have access to the chat box for some reason, then maybe raise your hand and we might unmute you one at a time. We've got just a few more minutes left. So anyone have any more questions, please type them in now or raise your hand virtually, and we'll see if we can let you ask your questions. We've got just a few more minutes left and we're almost done. So far, just to let you know, Rob, we've got several people commenting that they're very thankful. They really enjoyed the presentation.
Well, I was certainly happy to give it, and happy to have people listen to this. It's a fun topic to, although it's not really, the colonization thing is not what I do for my career, but it's all part of a larger picture. Mars is a really big, interesting physics problem that's incredibly interdisciplinary. So I see there's a question, gut feeling about likelihood of life currently existing on Mars. It's a good one. I think that we have not ever drilled deep enough on Mars to get to a place where any life that would have existed wouldn't have been destroyed by radiation a long time ago. And this is why the European ExoMars rover that's going in 2020 is going to bring a drill that's going to go 2 meters down. So it is going to get to that layer where if life existed, life would be protected from those galactic cosmic rays. Now, whether or not that European rover goes to a place where any life, if it exists, is actually there, well, that's really a matter of, guesswork and luck. Certainly Mars has the right chemical ingredients to support life. We know that life can exist in some pretty extreme environments on Earth. It wouldn't hugely surprise me to find microbial life under the surface of Mars, but it also wouldn't surprise me if Mars had none.
Okay, so I think that's a good answer to the question of your gut feeling about the likelihood of life on Mars. We had a question whether or not, if people have further questions, would you mind if we pass those along to you? Email me or
do you want to wrap it up right now? I do see 2 more questions.
I do see 2 more questions. There's that was one of the questions, and the other one about solar wind doesn't. There are 2 questions here. Doesn't that make a difference as gases on Earth don't get that excited by the solar wind?
Well, actually, on Mars, the solar wind is mostly deflected around Mars, not by a global magnetic field, but just by the fact that Mars's ionosphere forms a conducting obstacle to the solar wind, and the plasma waves that initially would build up if the solar wind impinged directly on that ionosphere travel upstream and form this thing called a bow shock. And so the bow shock is a magnetic structure that sits about 2,000 kilometers away from Mars' surface, and that bow shock actually deflects most of the solar wind around Mars. So not much of the solar wind truly directly interacts with the upper atmosphere. It's more that when the solar UV radiation creates an ion in the Mars upper atmosphere, that there's that it can still feel the electric field of the solar wind and can be accelerated away from Mars. So that's that. And there's one last question about the InSight drill. InSight's drill is a heat flow probe, and I believe it's going to go a couple of meters down, but it's not going to have any sampling ability. It's just going to be measuring the difference in temperature between the bottom of the heat flow probe and the top of it in order to understand the rate at which heat is escaping from Mars, which will tell us important things about the structure, both physical and the temperature of the Martian interior, but it's not going to shed any light on the life question.
Thank you. I think that's the majority of the questions, but Tom has just posted an email address that people, if you have additional questions, folks, send it to maven2mars@gmail.com, maven2mars@gmail.com, and we will see about getting answers to you. Please join us, everyone, in thanking Dr. Rob Lillis for tonight's presentation. I know that we all enjoyed it very much, and we look forward to seeing you in the future. We will have our next presentation in just a month. Our next MAVEN Outreach presentation will be in September, and we'll be sending out announcements with the detailed description for that shortly. We'll in the next week or so. Again, thank you folks for joining us this evening, and thank you so much to our speaker. The next MAVEN presentation will be on September the 19th. And we'll be posting the recording such as it is in the next few days online.
Thank you.
Thanks, Rob.
Okay, thanks everyone.